In linear algebra, the Gauss method is a classical way to solve system of linear equations. The principle of the Gauss method is to perform elementary transformations over a system of linear algebraic equations. And with the help of this transformation, system of linear equation is reduced to an equivalent system of echelon form, from which variables can be found. Gauss method is the most powerful and versatile tool for finding solutions to any system of linear equations. As you remember, I recorded video with Kramer's rule and matrix method, but these methods are unsuitable in cases where the system has either infinitely many solutions or is inconsistent, which means doesn't have solution. So therefore, the Gauss method is the universal method that can be applied, can be used for solving system of linear equations with one solution, with many solutions, and with no solution. Okay, so let's use example, and I'll go over step by step how we're going to apply the method of Gauss. The core of this method is the same echelon the reduction of matrix. So we have to bring to echelon form and then rewind it back to the format of system of equation and find our unknown variables. Okay, and as they say, it's better one time to see than 10 times to hear. Let's start working. So we have 3x plus 2y minus 5z is equal -1. Okay. Next one is 2x minus y plus 3z is equal 13. And next, x plus 2y minus z is equal 9. This is our system of linear equations that we are going to solve. Now, in this case, we are going to use extended system matrix. Let me real quick cover it so you would understand what means system matrix, what means extended system matrix. So, to write down this system of inequality in the form of matrix, I'm going to get 3, 2, -5. So I'm writing down coefficients 2, and pay attention, x under x, y under y coefficient, and plus 3, and then 1, here plus 2, and minus 1. Now this form we call system matrix. The matrix composed only of the coefficient of the unknown in this example of system matrix. Now, but we are going to use extended system matrix to solve this system with the method of Gauss. And the extended system of matrix is when we include it's the same like system matrix, but plus the free members of the column in this case. So let's see. We wrote down all coefficients, but the first equation is equal -1, right? We write down here -1 and separate with vertical line, so we know those are results. Second equation is equal 13. The third equation equal 9. So this is extended system matrix, and this is the one we are going to use. All right. So, well, let's from here form echelon matrix, echelon type of matrix. So what does that mean? Just to remind you real quick, we are going to take by diagonal these numbers. Those are going to be our leading coefficient. And underneath of this leading coefficient, in the column, we are going to get here zeros. These two are going to be 0 underneath the second leading coefficient, which is -1. 2 is going to be equal 0, and the third one, it's only leading coefficient. Okay? So let's get going. So it is a good habit to have the first leading coefficient, in this case we have 3, to have it as a 1, because further operations with this first row will eliminate the chance to get fractional numbers. So that's why we always trying to get the first number as a 1. So what am I going to do here? My first line has 1, right? In the same column, right? This one. So I'm going to switch third line with the first line. R1, I'm switching with R3. And we are getting 1, 2, -1, yeah. So this is gonna be 9. Second row, second line stays the same. 2, -1, 3, and 13. And the third one, the first line comes as a third one, right? 3, 2, -5, and -1. Okay. Next, so I have 1. This leading coefficient 1, I got it. Now my job is the rest of the column, 2 and 3, for that leading coefficient 1, turn to 0. Okay, what am I going to do here? I'm going to do the following operations. And I'm going to do it 2 operations at the same time because they are not related. So if I make this one 2 and subtract 2 minus 2, the second line minus first line, that will be multiplied by 2, I'll get 0, right? Instead of 2. So first one, I'm going to do R2 minus twice R1. And as a result, I will get, instead of 2, I will get 0. And the same thing I will do with R3, because my the third line is starting with 3, so I'm going to R3 minus 3 times R1. Okay, and first change, I'm writing down where R2 is, and second change, I'm writing down where R3 is. Okay, so this is this way I will get these zeros in the line of, 1 second, okay, in the line of 2 and 3. So what do I get here? Let's do first operation first. I need to multiply first line by 2 to do this operation, right? Twice R1. So it's going to be twice, it's going to be 2. This is going to be 4. This is going to be -2. This is going to be 18. Okay, let's do now R2 minus R1. So First one, I rewrite the way it is. 1, 2, -1. This is 9. So second line, I'm changing color because there are going to be changes. So this 2 minus this 2 is going to be 0. Next, this -1 minus this 4 is going to be -5, because -1 and minus 4 is going to be -5. The third one, I'm going to do 3 minus -2. I will end up adding, right? 3 minus -2, I'm getting 5. And lastly, 13 minus 18. And I'm getting -5. Next, I'm doing the second line change. Let me clean this. Third line. Let me clean this drafting. Now I need to do R3 minus 3 times R1. So I'm going to multiply 3 times. So 1 times 3 is 3. It's the first line. 2 times 3 is 6. -1 times 3 is -3. And 9 times 3 is 27. Okay? So what do we get from here? 3 minus, let me see, 3 minus 3. I am getting 0. As you can see, we successfully got 2 zeros under 1, right? And that's what echelon form means. Under every leading coefficient, we have to have 0. Next, 2 minus 6. We are getting -4. Next, -5 minus -3. We are getting -2. Okay, and -1 minus 27, we are getting -28. Okie dokie, we got that also. Next, we took care of entire column under first leading coefficient, moving to second leading coefficient, which is this 5, -5. Okay, so in which if leading, why do we say leading coefficient? All manipulation now have to be with line 2, because leading coefficient in the line 2. Okay, so we are not touching line 1 anymore. We are doing manipulation with line 2. When we were trying to make 0 the lines under this leading coefficient 1, so all manipulation I was doing with the line 1. Now my leading coefficient in the line 2, then I'm going to do all manipulation with line 2. Okay, I forgot to clean this. Let me clean it to keep it clean, the matrix. Okay, so we have -5. So what can I do? When you are solving, although if you just convert the form, echelon form of matrix without any given system of equation, well, you can leave it -5. But if you are doing a system of equation, it's better to simplify as much as possible. For example, the second line is -5, 5, -5. I can reduce by 5, right? Why is that? It's like instead of having 2x is equal 6, I'm writing down x is equal 3. That's what it is. Okay? So, what am I going to do here? And I'm going to cover two operations at the same time, because they are not related anyhow. So second line I can divide by -5, because I want to get rid of negative sign. So R2 divided by -5, and write down in the R2, of course. And at the same time, are free also. Look here, negative 4, negative 2, negative 28. I'm simplifying, dividing by negative 2. Are free, dividing by negative 2 and rewriting into are free. Okay, let's see what we will get here. So, first line stays the same. 1, 2, negative 1, and 9. Second line, I'm dividing by negative 5, right? First is 0. Second one divided by negative 5 is going to be positive 1. Let me change the color. Third one, 5 divided by negative 5, we are getting negative 1. And the third one, the available term, meaning result, we are getting positive 1. Next, R3 dividing by negative 2, it's going to be 0. It's going to be 2. It's going to be, how much? 1, positive 1, yes. And 14. Okay. So, I got 1 here, leading coefficient, which is very good, because this one we're going to identify y, right? Let me write down so you would know this first line x, this first one is going to be my x, this one is going to be my y, and this one is going to be my z. That's why echelon form, it's representing leading coefficient, represent unknown variables x, y, z. Let me clean this mess. Okay, so now I need to get 0 under this second leading coefficient 1, so this one. Okay, what can I do? This one multiply by 2 and subtract from third line. Let me see. We're going to do R3. Remember I said simply the coefficient in the line 2. We are doing all manipulation in the line 2. So 2 R2. So first line we leave it alone. 1, 2, negative 1, 9. Second line we also leave alone. 0, 1, negative 1, 1. But because we need third line minus twice second line, let me multiply here by 2. It's going to be 0. This is going to be 2, negative 2, and here I get 2. Yes? So, which means third line, 0 minus 0, it's going to be 0. And then 2 minus 2, it's going to be 0. And then 1 minus 2, right? It's going to be 1 minus negative 2. Hold on. Did I mess up? No, of course. Negative 1. It's going to be 3. 1 minus negative, 1 minus negative 2. So it's going to be, we will end up 1 plus 2, so 3. Okay, I'm sensing something is wrong. And 14 minus 2, this 14 minus 2, we are getting 12. If it would be easier, maybe I should have written down this on this side, so it would be easier. 0, and then 2, this is negative 2, and this is 2. And then subtract this minus this minus this one minus this one, and then minus this one. Okay? All right. and we get matrix. Okay, so next, although I have already echelon matrix, but I'm going to bring to reduced form of echelon matrix, because why? I have in the third line, I have 3 and 12. I can reduce by 3, right? I wanted to say 4. So what am I going to do here? Row 3, reducing by 3. And I'm getting 1, 2, negative 1, 0, 1, negative 1, 0, 0, by 3 is 1, and here will be 4, 1, and 9. Okay, let me highlight on this piece, because those are changes we did. Oops. This is reduced echelon form, okay? When we just reduce it as much as possible. Just like I did with the second line, I divided by 5. Okay, so this is what we got, echelon form. So from here, we are getting back to our system of equation, but with much simpler form. Let's see. We are getting coefficient x is 1, so I'm getting x plus 2y minus 1z, or I don't put any 1, just write down z, and it's equal 9. Remember, I am writing down here, let me see, this is my x, this is my y, this is my z, right? Okay. Second one is going to be, I don't have x, it's 0, but I have y minus z is equal 1. And third one, I have only z is equal 4. Now look, from this equation, we arrive to this equation, system of equation. And there is nothing much to do. So z is equal 4. Next, that means y is equal z plus 1, and it's equal 4 plus 1 equal 5. And from here, x plus 2 times my y is 5 minus 4 equal 9. No, I mean equal 9, yes. And x from here is equal 3. So our answer, x is 3, y is 5, and z is 4. Let me write down. 3, x, y, z. So in the alphabet order, right? 3, 5, and 4. So this is how we solve system of linear equation. This is much more effective when more complicated system of equations. Okay, now, like I said, unlike Kramer's method, with Gauss method, you can solve also, you can find give solution to system of equations that have either many solutions or have no solution. How we are going to figure out which one is no solution, for example. Let's say, I'm not going to go through the whole process, but let's assume we have system of equations, linear equations, and we need to solve it. So we did all this simplification, we brought to the echelon form, which is, let me pick some different color. Well, okay, I use this color. And I got negative final my form of this matrix is negative 1, 0, 1, 7. And I have 0, negative 1, 2, 9, here is 14, and here I'm getting 0, 0, 0, 0, and I get 2. What am I getting from here? I'm getting that my z, if I write down in the form of equation, it's going to be, let's say, negative x plus, the second one is 0, so it's going to stay 0. It's going to be plus, let's say what, x1, then plus x3, because x2 is going to missing because it's 0, right? Let me write down x1, x2, x3, x4. Here we have such the variables. So we are getting x1 plus x3 and plus 7 x4. This is equal 7. And then x1 in the second line is 0. We are getting negative x2 plus 2x3 and then plus 9x4. It's equal 14. And the third line we are getting 0 is equal 2. Then go figure. If you can prove that 0 is equal to, you will become next Nobel Prize winner. So which means that tells us that this system of equation is inconsistent, has no solution. Accordingly, to get many solutions, you would get 2 is equal to, right? That would be many solutions. Okay, that's all. This is only method of Gauss. There is also Gauss-Jordan method, so don't get confused. It's a little bit modified method, Gauss-Jordan. This one is purely method of Gauss. Another thing, I think yes, very important thing I wanted to mention, and I should have mentioned it at the beginning, but I forgot, my apologies, but I'll tell you now. If one thing, when you get matrix from the system of equation, you are allowed to do all these transformations over these the rows or lines. But another thing, if you are given abstract some matrix, let's say you get some matrix, negative 4, 5, 7, 3, 6, negative 1. You don't have right to do these transformations, because this matrix does not represent any equation, any system of equation. It's just a matrix. Okay? You can take and manipulate and get this and that. All you can do, whatever operation you need to do, get inverse or multiply by scalar. Or you have to have another matrix to add them, or another matrix also to matrices to subtract, but not these manipulations over these lines. This is crucially important to remember. Okay, I am done. See you next time.